Hello everyone and welcome to lecture series of food processing equipment design. So in today's class we will learn about design of shell and tube heat exchanger. The shell and tube heat exchanger, as the name suggested or as the name indicates, that it is a heat exchanger which is consist of shell and a tube. Okay, a bundle of tube will be there which is inserted inside the shell. So one fluid will be flowing inside the tubes, another will be flowing inside the shell, and heat exchange between them. So it is one of the most commonly used heat exchanger in various industries, and due to its simplification, because it is one of the most simple type of heat exchanger, due to its simplicity, it is used in various industries. Okay, in this lecture, mainly we will consider about how we design the heat exchanger. We will learn about the components of heat exchangers, and then we will design each component of heat exchanger one by one. And we will also consider the thermal design consideration about heat exchanger. So without wasting further time, let's start the lecture. So in this lecture, we will mostly see the introduction to shell and tube type heat exchanger. Then we will see the various components of shell and tube heat exchanger. After that, we will see the design consideration of shell and tube type heat exchanger. Then we will see design parameters in details. So coming to the introduction, what do you mean by shell and tube heat exchanger? As I have already discussed, it is a heat exchanger in which is consist of a shell and tubes. So one fluid will be flowing inside the shell and another fluid will be flowing inside the tubes. Okay, and the heat exchange between them. Okay, it deals at for conduction type of heat exchanges. The shell and tube type of heat exchanger are one of the most versatile type of heat exchanger, and they are used in the process industries, in conventional and nuclear power station, steam generator and food industries as well. Shell and tube type of heat exchanger provides relatively large ratio of heat transfer area to the volume. This is important, that it provides relatively large ratio of heat transfer area to the volume. So after that, because of its simplicity in design, it is very easy to clean the components of shell and tube heat exchanger. And the design of shell and tube heat exchanger is very much simple. So we will see the design in later part, but before that, let's see various components of shell and tube type heat exchanger. Here in this slide, we can see a shell and tube type heat exchanger, or in short we call it as STHE, shell and tube type heat exchanger, STHE. So here we can see the various components of shell and tube heat exchanger. So the thing is, the shell and tube heat exchanger is a very simple one, and its design is also very simple. Okay, there are not much complication in designing the shell and tube type heat exchanger. Only there are few major parts. So first one is shell, which we can see here. Okay, the shell we can see here. The next one is tubes, which is inserted inside the shell. Okay, and this is tube side. So depending upon the fluids flowing inside shell or tube, we divide shell and tube heat exchanger in two components. First one, tube side and shell side. Okay, so from here we can see in presentation. From here we will divide shell. This will be tube side and this will be a shell side. Okay, and there will be a front portal. There is end, or we can call it as head, tail, and then we are having tube side fluid inlet, tube side fluid outlet, shell side tube inlet, shell side tube outlet, and these are the uh, components to hold the shell and tube type heat exchanger. This is for increasing the length of the shell and tube type heat exchanger. This is also known as expansion joint. Then next one is, this is shell, of course, and these are the baffles. Baffles is also very much important component in shell and tube type heat exchanger, because baffles are mostly used to create the turbulence inside the shell and tube heat exchanger. And the turbulence flow is very much important in proper working of shell and tube type of heat exchanger or any type of heat exchanger, because it increases the heat transfer area and heat transfer properties. It basically it increases U, which is heat transfer coefficient. So that's why we always prefer to create a laminar flow instead of, we always prefer to create a turbulent flow instead of laminar flow. So now the problem here is that we can't draw this diagram in our exam. Correct? It will be very difficult to draw this type of 3D diagram. So that's why I came up with a simple diagram which looks like this. This is a line diagram of shell and tube type heat exchanger. This is a straight tube type heat exchanger with one pass tube side. So we will know about this later. What is one pass, what is two pass, what is four pass, six pass. This we will understand in later slides. So here the important things are, so this is tube sheet which holds the tubes from both the ends. So there are two tube sheets which will hold the bundle of tubes. So this is inlet for the tube. This is outlet for the tube. Now this is inlet. This is inlet for the shell side fluid. This is outlet for the shell side fluid. These are the bundles of tubes, and this will be the flow of shell side fluid, and this will be the flow of tube side fluid. Now let's discuss about baffles. Baffles are very much important, as we already discussed, because it creates turbulence inside the shell and tube type heat exchanger. So this is baffle. Here we can see this is baffles, and this is shell. Baffles, shell. So this will be the simplest type of diagram which can represent the shell and tube type heat exchanger. Okay, coming to next slide. So let's start designing shell and tube type heat exchanger. So when we are going to design shell and tube type heat exchanger, we will see the basic design procedure. So what is the basic design procedure? That a heat exchanger must satisfy two conditions. First condition is heat transfer requirements, or simply call it as duty. The first condition is heat transfer requirement or duty of heat exchanger. Okay, it must satisfy the heat transfer requirements. Second one is allowable pressure drop. It should have some pressure drop. Okay, that pressure drop should be in allowable conditions. Okay, allowable value. It shouldn't be very high. Okay, the pressure drop shouldn't be very high, or it shouldn't be very less. It should be allowable. We should allow a little bit of pressure drop in heat exchanger. So there are a few steps we generally consider for designing of heat exchanger. So first one is identify the problem. Okay, for example, we need to design heat exchanger. So for that we have to understand which product we are going to use. Okay, what are the characteristics of that product? What are the temperature we need to get? What will be the flow rate of the product toward the tube side, toward the shell side? So what will the velocity? So all these things we should understand before designing the shell and tube heat exchanger. So first one is identify the problem. The next one is select and heat exchanger type. Then we have to select the heat exchanger type. Which type of heat exchanger will be better to designing that heat to solve that problem. Okay, either it will be plate type heat exchanger or the shell and tube type heat exchanger will be useful. Okay, so in this case, in our case, in today's lecture, we are going to design shell and tube type of heat exchanger. So next one is calculate the initial design parameters. So initial design parameters are like how much heat load it should generate, how much inlet temperature should be, how much outlet temperature should be, that we have to calculate. After that, we have to calculate the performance, the thermal performance. After considering the initial calculation, design parameters, we have to go for thermal performance. Okay. In initial design, we will also see the length of heat exchanger, wall diameter of the shell, diameter of the tubes we are using. Whereas in calculation of thermal, we will see the basically related to the heat properties. Okay, then we evaluate what we have designed. Is it suitable for our purpose that we are going to solve for? Okay, because there are certain errors, certain consideration which we have to take in consideration, which we have to take as an input, and we have to design. And while we are designing that, we should see whether it is okay to take that whatever we are designing to take that much uh, capacity of heat exchanger, or the parameter we have decided, is it okay to design for that parameters. Okay, so that is evaluation part or optimization part. If that is not fulfilled, then we will go to the step 3 again. We will calculate the parameters again. Then we will calculate the thermal parameters again. Then again we evaluate it. So this is how we are basically going to design a heat exchanger. In this case, we are going to design shell and tube type heat exchanger. So next we will see first one in designing of shell and tube type heat exchanger. First comes the shell design. So the shell is the outer part which we see here in this component. The shell is the outer part which consists shell side fluid, okay, which holds one fluids and also it holds the bundle of tubes. Shell design. If we start with the design of shell type fluid heat exchanger, so first comes the shell design. We have to design the shell. How we design the shell and what is shell? Let us discuss here. So shell is the container for fluids and the tubes placed inside it. It works as a container. And shell diameter should be selected such that it gives a close fit of the tube bundle. So we have to design here for diameter of the shell. That is, let me take the pen please. So when we are designing the shell, so we'll design for DS, that is shell diameter. I'll write in short, shell dia. Then the second one is we will design for shell thickness. Okay, which is thickness of shell. So as I have discussed here that a shell is nothing but a vessel or a container. So designing of a vessel thickness, which formula we use? We use hoop stress formula. We know that sigma L is equals to P D by 2. In this case, since we are designing the shell, so in this case, sigma L is hoop stress, P is the pressure inside the shell, D is the diameter of shell, T is nothing but the thickness of the shell. So this is the formula we basically use to design for the thickness. Whereas the formula will be different for designing the diameter of shell and tube type heat exchanger. So that formula we will see later, because when designing for diameter, we should consider other components also, like diameter of the tube, size of the tube holdings, or what we call it tube plate, and the pattern of the tubes, pitch of the tube. These are some components or the parameters on which our design of diameter of shell depends. So that we will see in later. So here we have seen the thickness, how to decide the thickness of the shell and shell shell and tube type heat exchanger. Sorry for that. So the clearance, usually I was talking about the bundles inside. So diameter should be very close to the bundles so that it contains the bundles. So the clearance between the tube bundles and the inner shell wall depends upon heat exchanger type and the pitch and the number of baffles, type and size and etc. So next come after shell. Next come tubes. So tubes are generally, let me draw tube, are generally, if we consider one tube, so it looks like this. The diameter of tube is generally of 8 to 15 mm. The tubes are usually very mm. Tubes are usually very small. So why we keep it small? Because it gives the greater area to volume density, but it also limits the purpose of cleaning. So smaller the tubes, difficult the cleaning, but better the area to volume density. So why we are talking about here area to volume density? Because we know that when we are heating something, the equation governs is Q is equals to UA delta T, where area is very much important factor. Okay, so if anyhow we are increasing the area, okay, so our heating Q will raise. Okay, so that's why area is very much important here. That's why we are talking about greater area to volume density. But again, if we like decrease the further size further of the tube, it will be very difficult to clean it. And also, the most common type of most common size of tube is 3 by 4 of inch or 1 inch. That is most common. And the most efficient condition of heat exchanger is to have maximum number of tubes in the shell to increase the turbulence. Turbulence we have talked again in previously. Again we are talking about turbulence because turbulence is very much important to increase the heat transfer rate. So the tube thickness should be withstand the internal pressure and have corrosion allowances. Why corrosion allowances or fouling allowances? Because we know that with time there will be fouling inside the tube or outside the tube because of the material flowing inside. Correct. So here we can see that if we give the allowances, then our design will be justified for much longer duration. If we are not giving some allowances, then after a certain time our design will fail. Okay, so that's why we should provide some allowances for fouling or corrosion, whichever is happening inside heat and shell and tube heat exchanger. So talking about, we have talked about the diameter. Okay, now another important component in designing the tubes is length, L. So when we talk about length, so there are usually standard lengths, okay, for tubes inside the shell and tube heat exchanger because it will facilitate the design process. Okay, the tube length are commonly used is 6, 8, 12, 16 or 24 feet. They are very much common. And the longer tube reduces the diameter of shell. That is common because the area will be constant for the like QA delta T. If area is constant, if we are increasing the length, the diameter will reduce. Okay, because we are putting less number of tubes. But what will happen if we increase the length of the tube? It will higher the shell pressure drop. Like pressure drop will be high. Pressure will reduce inside the heat exchanger. So we have talked about allowable pressure drop in previous slide. So from here we can relate. Okay, that allowable pressure drop should be there. So if we increase the length, the pressure will reduce. So if we talk about generally, these tubes are made up of stainless steel, brass, bronze, copper, and an alloy of nickel and copper. So after the tubes, we have to see about tube pitch. So tube pitch is another important parameter in designing a shell and tube heat exchanger. So so this is our tube we have designed. Let us consider its outer diameter as D. Okay, when we talk about the tube pitch, Then we talk about the arrangement of tubes inside the shell and tube type heat exchanger. So, for example, our arrangement is square type. Square type arrangement is like this. It means all the tubes are in square. It makes a box. Okay, it makes a box like this or square like this. So this is a square type arrangement in shell and tube type heat exchanger. So talking about the box, so what is pitch here? So what do you know? We know D naught. What is D naught? Diameter. That is D naught. So distance between the center of one tube to another is known as P. That is tube pitch. Okay. And we should maintain certain ratio when we are designing the shell and tube type heat exchanger. So we can see the close pitch, small value of P by D naught for increase the shell side heat transfer and the surface compactness, and open pitch or large values of PT by D naught for the decreased shell side plugging and ease the shell side cleaning. Generally, the what is the value ratio we take is 1.25 to 1.5. Our P by D ratio, PT by D naught ratio generally lies between 1.25 to 1.5. And the tube are close to each other, less than 1.25. Okay, so it should be less than 1.25 of D naught for better design. Then let us revise again. What is tube pitch? Tube pitch is the shortest center to center distance between two adjacent tubes. So generally the tube pitch varies according to the variation we are putting. Like what are the general variation or arrangement we put inside a cell and type heat exchanger is, first one is square one we have seen here. Okay, sorry. Square one. First arrangement is square, we have already seen. Second one is triangular one. And the third one is rotated square. Rotated square. How it looks like? So we can see this will be the triangular arrangement of the tubes. And this will be the rotated square arrangement. This will be the rotated square. Here again. So this is how we design for tube pitch. After tube pitch, let's talk about number of tubes. Number of tubes that can be accommodated in a given shell is called as tube count. It depends upon the internal diameter of shell, outer diameter of tube, and tube pitch, tube layout, and number of tube passes. So these are the various components which decide how many number of tubes we are putting. So if I shorten it, The number of tubes depends upon the flow rate and level pressure drop. These are the two components basically it depends upon. And number of tubes is selected such that the tube side velocity should be in the range of 0.9 to 2.4 meter per second. And similarly, the shell side velocity should ranges from 0.6 to 1.5 meter per second. So, lower the velocity limits the correspondence to the limiting the fouling. Okay, so lower the velocity, the flow will be laminar. If the flow is laminar, fouling will be more. If fouling will be more, effectiveness of heat exchanger will reduce. So all these things are interrelated. So if in brief I explain that number of tubes depends upon internal diameter of shell, tube outside diameter, tube pitch, tube layout, number of tubes passes, etc. So coming to next slide. After designing the number of tubes, we go for the tube passes. What do you mean by tube pass? So if we go by definition, then a tube pass is when a liquid flow all the way across from one end to the another end of heat exchanger. Okay, from one end to the another end of heat exchanger, when a flow comes, that is a pass. So generally we say about 1-2 type of heat exchanger, 1-4, 2-4, okay, or 1 pass, 2 pass, 4 pass type heat exchanger. So how we classify it? Okay, for that let us take some example. Suppose this is shell of suppose this is shell of shell and tube type heat exchanger. We have to make tubes now. This is one end. This is outlet for tube. This is inlet for shell. This is outlet. Correct. So if it is 1, 1. So how we can make it 1, 1? So our flow will be like this for tubes, and for our shell it will be like this, shell flow. So this is 1 type. Okay, only one single flow of tubes, one single flow of shell. Now same if we want to make 2 flows, then what we will do? We will provide an idle in between. Now what will happen? Our tube side fluid will go and come here and exit from here. This is for 2 pass type of heat exchanger. Similarly, if we go for 4 type, okay, then we divide our shell in 3. Okay, so our tube side fluid will travel like this, like this, like this, and it will end here. Okay, so this is 1-4. How we make 2-4 pass type? Here, then we will divide tubes like this. Okay, so what will happen then? Our whole shell side fluid will pass like this and exit from here. This is 2-4. So hopefully this is clear. What is 1 type? What is 1-2? What is 1-4? What is 2-4? The number of tube passes depends upon the available pressure drop. Like if our fluid is traveling more distance, the pressure drop will be high. The higher the velocity in the tube results the higher heat. And it also increases the U value. overall heat transfer coefficient. But again, we have to compromise with pressure. The pressure drop will be very high. Okay, so pressure drop and Q value are interrelated to each other. Coming to next slide. So next slide is about tube to head plate connections. What do you mean by that, tube to head plate connections? So we know that we are giving the bundle of tubes. Correct. So for bundle, so supporting that bundle of tube, we have to provide some head plate. So this we are seeing in this slide is head plate. Okay. Head plate done two work. It performed two operations. First one, it holds the shell side tube, shell side fluid at one end and tube side fluid at one end. Second one, it also provides the stability to the tube bundles. So the tubes are arranged in bundle and held header in the place by head plates. So this will be the one and this and another end will be the another one. Anyway, this is the U type shell and tube type heat exchanger. So there is only one head. If it is two, so this is header one, this is end one. This will end plate, this will go known as head plate. Where the fluid is inletting for tube side fluid, that is header, and where it is exiting, that is end plate. So the number of tubes that can be placed in a shell depends upon, we have already seen that, tube layout, tube outside diameter, which is known as DTO or DO simply, then tube pitch, then number of passes, then shell diameter. And when the tubes are close to each other, the head plate becomes weak. Why so? Let us talk about that. Suppose this is our head plate. Now, if we are having, suppose in this area we are having 4 tubes. Generally we have in the range of 80 to 150 tubes. But for make it simpler, let's have 4 tubes. Okay, we are having 4 tubes. At that time, we make 4 holes. Then their strength will be S4. Okay. Then let us consider strength is S4. Now, if we make 4 more holes, space for 4 more tubes, then the strength will be S8. S8. So which strength will be higher? Since we made more holes in this plate, so strength of S4 will be more than the value of S8. That is why when we make closer spacing of tubes, we accommodate more tubes and it becomes difficult for the plate, head plate or the end plate to hold it. That's why again we have to consider this when we are designing the shell and tube type heat exchanger. After this, let's talk about baffles. So baffles are the components which perform two functions. First function is support the tubes. Second one is divert the flow. So a part of head plate or end plate, the support is given by baffles also. Okay, which are rigid and it prevents the tube to sag or vibrate during operation or sagging, and it divert the flow, and diverting the flow, how it helps, it will create the turbulent flow. Okay, it obtains the high transfer coefficient. So if the flow is turbulent, then we'll get the higher heat transfer coefficient. And how we optimize the baffle spacing. So baffle spacing will be generally 40 to 60% of the shell diameter. And what do you mean a baffle cut? So this here we see the baffle cut. Okay, if we look here, shell and tube type heat exchanger like this. So inside this, the baffles will be like 1 and 2. The space which is left here is baffle cut. Okay, so the space left between the end of the baffle and the shell diameter or shell boundary is baffle cut. So how much baffle cut we should provide? It generally varies from 25 to 35%. So next, after baffle cut, we will see the types of baffles. First is, here in the diagram we can see this is segmental cut baffle. So a segment of a circle will be cut, as you can see here. This is segmental cut baffle. Disc and ring type baffle, second one, in which we will form a disc and another baffle will be there which will form a ring, which will be like this. Okay, this will be inside baffle, this will be outside. This will be ring, this will be disc. And third one is orifice baffle. Here we can see there are spaces. The tube will be round. Okay, it will come like this. And there will be space between the tube and baffle. So this space will create the orifice. Okay, this will be the orifice type of baffles. So there are three types of baffles again: segmental cut baffle, then disc and ring type baffles, then orifice baffle. So baffles are used to increase the fluid velocity by diverting the flow across the bundles to obtain the high heat transfer coefficient. So we already discussed about baffle spacing also. Thank you. This is it for today's lecture. Let us revise some components, designing of some components in shell and tube type heat exchanger. We have discussed how to design the shell and tube type heat exchanger, how to design the tubes, then what is pitch, what is tube layout, what is tube count or number of tubes, then what are the tube passes, what is tube sheet or header plate or end plate, and the last three baffles. So there is also one consideration for fouling. So whatever the heat transfer or whatever the size we are getting for the tubes, we multiply it with the factor of 0.25 or we multiply it 1.25. That is for fouling. So generally the fouling factor ranges from 1.25 to 1.6 depending upon the properties of our material we are using. That is consideration for fouling factor. So here, if we consider all those things, we are able to design the shell and tube type heat exchanger. So we will solve the numericals of shell and tube type heat exchanger in next class. So hopefully you understand this lecture and you like this lecture. We will meet for next lecture very shortly. Thank you.